We live in an age where portable laser blasters can shoot down drones. Yeah. Can slice through flesh.
My wiener!
Precision weed the garden. Weld a huge variety of materials. Interface with robotic CNC droids. And efficiently remove paint and rust without any need of chemicals. And all of which we'll be testing if this laser can do it. This technology is officially and slightly worryingly becoming commonplace in garages across the world. And that's because they're now affordable. So now, since the last video, X Laser Labs have notified me on the manufacturing progress of their Kickstarter campaign. If you go on their main channel or their Facebook page, they've been notifying us of their progress. And they've assured me that backers will start receiving their machines in May. But I do understand that a lot of people still don't trust the hype of this technology. There are actually a lot of scams going about saying that you can get one of these for about 40 quid. And apparently people are expecting one of these and receiving a soldering iron. No, this is about 2.5 grand. And the technology has actually been in circulation for a number of years now, mainly in industry. Those, however, have costed about 10 times that amount. But listen, I've managed to get hold of another one of these, and I'm going to offer it to one of you guys for just a £5. I've set up a competition in the description of this video. It's hosted by Raffle, which is a British company. It's approved by YouTube and full of reviews of previous winners. And also to help you out, I've put the exact link to this specific laser in the description, as well as all the other tools that I've been using in this video if you want any of them. But because honesty and transparency is the key to this channel's success, let's objectively pick this apart and see what's wrong with it. And the first thing I want to do is test it against my other welding equipment. So I've got these plates to test on. You can see I've also sanded the faces to take the mill scale off, and also so those faces are dead flat with each other. So we're going to start with the laser. Then we'll do stick welding, which is actually my favourite type. And specifically, I'm going to be using 3.2mm 7018 SIF electrodes. These are industrial standard, intended for structural loads. So after that, we'll try MIG welding, which is actually going to be mag welding. MIG stands for metal inert gas, but mag stands for metal active gas. And I'm going to be using synchronous settings, which means it's all kind of automated for me. So the active gas is a 12% mix. That's 12% carbon dioxide, something like 2% oxygen, which boosts the intensity of the arc, and the rest being argon gas. And I'll be using a 0.8mm mild steel wire on it. Lastly, we'll do a test with TIG welding. This is my CK Superflex with a number 12 gas lens. If you don't already, TIG stands for tungsten inert gas welding. The tungsten being this needle tip here, which can withstand extremely high temperatures. And I'll use pure argon as gas shielding. So I'm going to get these tacked up to do what's called a fillet weld. So I'm going to do a weld either side. We're going to do a cut and etch it so we can see the penetration. And then with the rest, we'll do a break test and see how much of that weld is actually grabbing onto the material. Let's begin. Right, so I've got the laser set at 100% power. Something important to bear in mind, and that is just 700 watts of optical output. There are lots of lasers on the market, mainly industrial types, that go up all the way to 6 kilowatts. 1.5 kilowatts is probably the most common. So remember, we're running this off a domestic plug. So in the UK, that's 220 volts at a maximum of 13 amps. The power consumption is actually 2.5 kilowatts of electricity. If we want to use anything more powerful in our garage, then we need to install like 32 amp plugs and the correct breaker switches. So the frequency is how many times per second that 0.4mm laser pulsates between the width that you've got here. I'm using a 1.2mm wire, and I've set my wire feed to 7mm a second. I'm using a gas shielding for the laser also. Specifically, I'm using pure nitrogen gas, which is less than a quarter of the price to buy compared to pure argon gas. Just in case you were wondering, I'll give it a couple of tack welds first. Something that may also be useful to people is the temperature. We'll check the finish temp straight after welding. So then, weld number 1. Turn it around, do the back side. Right, so check the thermal imaging. Ranges between about 65 to 75 degrees Celsius. Let you have a closer look. So you can see it's so neat, but so small. I set the weld face to be 2.4 millimeters, and it's pretty much exactly that. With a 1.2 millimeter wire, I can't actually create a weld much wider than that. We can actually multi-layer it, so just keep doing lots of passes. I think you'll probably prefer one of the other methods. So for the rest of the welding, I'm using my Spiritus powered air respirator by Artex. So this feeds filtered air directly into my weld helmet, and I've got a choice of a grind screen or the welding screen. I guess they called it Spiritus because you look like a space marine. For the laser welder though, I'll be using the designated glasses. That's until I get a laser welding hood similar to this one. So for stick welding, I'm using my cheap and cheerful no brand inverter welder. It actually does TIG welding as well. I paid about 200 quid 10 years ago for it. So I'll get this ready just like before, and I'm going to set the machine to 130 amps. So we'll attempt to tack it to start with. Now restarting a 7018 is the hardest. To get around that, I tend to just break the end off a bit like that. There we are. We'll just chip away the slag. So far so good, let's do the other side. If we put on thermal imaging, you can see we've gone up to about 180 degrees Celsius. That's a lot hotter than the laser. But there you go, stick welding, cheap and cheerful, and if done right has superior strength. But obviously we'll test that shortly. And so now on to MIG/mag welding. You can see I've set it to synchronous MIG. We're using a mixed gas, 26 volts, 200 amps. The wire feed is preset. I can't actually tell you what the wire feed is. Setting up exactly the same as before, except instead of dragging like we did with the stick welder and laser welder, with MIG my preferred method is to push. And that way I can see exactly what I'm doing. Looking alright, it's a bit spattery, but that's common with MIG. You see that little line there? That's actually a really good sign we've got good penetration. So unfortunately on my stick welder shot, I didn't actually have the high temperature icon clicked because the MIG weld is saying over 400 degrees Celsius. Let's see what it's like up close. Right, so that was the first weld. We're measuring a face width of about 10 millimeters, and then that's the second weld. But overall, I'd be very happy with that. In fact, that's how I welded up my hydraulic press, and it's held up absolutely fine. Right, so for TIG welding, I've obviously switched the bottles around. So now we're running off pure argon. I've changed the polarity of the leads, and I've set to 160 amps. I've also given myself plenty of post flow as far as gas coverage goes. So I'm actually self-taught when it comes to TIG welding, but I must make a massive shout out to Jody from Welding Tips and Tricks. If you want to learn welding, it's his channel you want to be watching. But I want to also encourage any believers to send some prayers to this man. He's currently suffering from leukemia, but he's keeping his head up high. And despite suffering the treatment, he's still willing to share his knowledge. Jody is incredibly inspirational, and I would highly recommend watching his channel. All right, no pressure then. I'll try not to let you down. So there's a bit of colour in that, which indicates that it's actually a bit too hot. The best way to counter that might be to up the amps and go a bit faster. I'm going to stick with it for now, because I'm comfortable at that pace. Otherwise, maybe having a larger gas lens might help that. TIG welding is definitely very pleasurable. So unfortunately I let it cool down in between welding, but we got to about 170 degrees Celsius of heat there. So I feel like I did a bit better this time round. It looks a bit more cleaner, not as hot. compared to the other side. A key indicator if you've got the settings right is this heat affected zone just there. My thoughts are if the heat affected zone is more than the width of the weld, then you're probably running a bit too hot. As in you probably need to go a bit quicker and not necessarily needing to turn down the amps. But otherwise, I'm really pleased with how those welds came out. So before we do the destructive tests, I just want to bring some realism on this. The strongest weld in this case will simply be the biggest weld, which is probably going to be the MIG weld, although the stick weld does have better properties. So we're going to bear in mind that the laser weld is only 2.4 millimeters. What we really want to see is how deep the penetration of the laser really is, and if we've got actual fusion between the weld metal and the parent metal. I'll also get my microscope out and check to see if there's any porosity and bubbles in there. But to select the right method for the job, you really want to look at speed, dexterity, and level of skill required. It's my opinion that if you want to learn to weld, start with a stick welder. It's cheap, it's cheerful, but it requires you to be very observant and therefore it will make you a better welder. TIG welding requires a lot of skill, but it also gives you the most control in all sorts of situations. MIG or MAG welding lays down the most amount of metal, which if you've got a lot of welding to do, that's kind of what you want. A laser welder could well be the birth child between TIG and MIG. It's fast, it's accurate, and very easy to lay down perfectly. If small, pretty welds are what you want, a laser welder might just be the answer. It's not as agile as TIG, it's never going to be as strong as stick, and it isn't going to be as productive as MIG unless you've got like a 6 or 10 kilowatt version, in which case you're probably talking 100 times more in price. But anyway, let's destroy them and see what they're like. There we go, they're sanded to 240 grit now. Right, so for edge testing we've got a solution of hydrochloric acid. I'll then use a neutralizer, which is basically bicarbonate of soda and water, and then we'll take a really good look at it with a microscope. So we'll start off with the laser. You can almost see it without the etchant actually. Now I'll wash it off and take a closer look. Right, so what do we think? Right, so I've zoomed in as best as I can. So remembering that this is 6 millimeters thick. And if we follow this line all the way down to this corner, then from the center there to here, that is the throat of the weld, which looking at it is just less than a millimeter. However, going past that, the penetration is obviously a lot deeper at over 1.5 millimeters. All right, so I'll put that to one side, and what I'll do is I'll show you the microscope. So if we zoom in on one of these welds. Now it's hard for me to point this out to you, but you can actually see some sort of porosity on the surface of that weld. It doesn't look very different to the rest of the parent metal though. I'm not actually worried about it. See these little black spots? That's some sort of porosity. If I look on the other side, and we've got a big little wormhole there, you can see the line where the two parent metals touch and the area that the weld has got complete fusion. If I now try and look at the surface, so there we go, that's the surface of the weld itself. And there are tiny little pinholes, it looks like, but otherwise looks incredibly consistent and really well done. Moving on then to the TIG weld. Put a bit of acid on you. So then what can we see here? I am slightly concave on this side where I was running a bit too hot. This side's more flatter profile, which is better, but the penetration is actually very similar to the laser, I think. So let's try and zoom in a bit on that one then. Would you look at that? You can see a very crystalline formation in there, haven't we? Go to the other side. There's definitely good fusion of material. Maybe I'll try and measure that unfused bit in the middle. Right, so if we put the side by side, TIG welding and laser, you can get a better idea. Non-fused in the laser is 3.1 millimeters. TIG welded, that's unfused, is nearly 5 millimeters. Very interesting. Move on to the MIG and stick welds. This is the MIG weld now. Well, I can see that's got some interesting shapes in it. Well, that is hardly penetrated at all. About 6 millimeters of unfused material there. So although this hasn't penetrated near as well as the laser has, you've still got nearly 8 millimeters of fusion on either side. So looking closely with the microscope, you can see we've got a little bit of porosity, or what's known as a wormhole in the middle there. And if we draw a line from the edge of the material down to the bottom, we haven't got very much penetration at all. It seems fused, especially on that side, but if we look along here, can you see that obvious line going across, especially that little dark line? That is lack of fusion. That is just sat on the surface. That's not good at all, despite the fact that I laid this down on full power. That is really fascinating to see that up close, actually. And so lastly, we have the stick weld. So again, that says 5.9 millimeters, so there isn't actually much root penetration penetration, unfortunately. Right, if we look closely though. So although at the root we don't have much penetration, there is lots of penetration on the walls of the weld, and there is complete fusion all the way around. That is a very good weld. The only thing I will say is I definitely had my angles wrong just here. You can see I was aiming more at the bottom plate than I was the side plate. So now for the proper destructive test using my 30-ton press. And if you're interested, I did a whole video on this previously. So again, we'll start with the laser weld. Let's put that in here. And we'll flatten it until it breaks. So how are we doing? There we go. Well, would you look at that? So as you can see, it definitely took some deformation before yielding. Definitely taken a big gouge out of the parent material. And if we take a really good look at that bottom plate, you can see all the material has come off the parent metal and not the weld. That is an excellent result. I'm very, very pleased. And considering there are more powerful lasers coming on the market very soon, this has given me a lot of excitement on many projects to build with this. Right then, now for the TIG weld. Oh. Gosh, that took some punishment. Right, okay, well that is very interesting actually. The failure in this case is actually straight through the weld itself. I mean, it's taken a lot of punishment, but that is quite shocking. Right, so without giving it a few hefts from the hammer, I can't actually get that apart. But really, that fracture has told me everything that I need to know. Right then, next we'll try the MIG, mag weld should I say. Goodness me. Well, that has performed way better than I thought it has. You can see it's actually starting to tear away at the parent material and not the weld at all. That is way stronger than I thought it was going to be. Incredible. So lastly then, we'll see how well the stick weld has performed. Oh my gosh, what was that? Oh, that's it. So that hasn't surprised me at all. 70-18 welds are super duper strong. You can see it's just tearing away around the weld at the parent metal. But to know your welds can take this kind of punishment, that's really good to see. I'm really surprised at the TIG weld cracking through the middle though. So I thought I'd done quite a good weld with that, but if you're a professional welder, let me know what you think. Now for the size of weld that the laser produces, and bearing in mind it's only a 700 watt output, I think that's really good. To have that level of deformation before anything significant breaks, and then it was the parent metal itself and not the weld. I'm very, very happy. Stick welding will always be my favourite process. I just love anything that does the job and is cheap. I mean, how could you ever complain about that? So I think the next logical step is to do an actual project with this. And what better than to build an actual welding trolley? So it's not just kicking around on the floor or on the table needlessly. So very quickly using CAD software, I came up with this design. It can carry a full-size bottle, the wire feed, the laser welder itself, and another machine if necessary. So I'm actually doing all the cutting on my driveway using one simple tool. So that's because box section like this comes in over 7 metre length, which of course I can't fit in my workshop, so I have to do the cutting outside. So now I've just got to mark out where the next cut line is, clamp on the jig like so. Perfect and accurate it seems pretty much every time. And just so you know, I'm not sponsored by these guys in the slightest. I wish I was, because I absolutely love their tools. But to give you some context on why I'm showing you this, I've chosen a left-facing blade. Because I'm right-handed, I can now see the cut very accurately. And I've also got a blade that is specific to metal cutting, that is 48 teeth. And as you can see, for straight cuts, this is far quicker than a laser or plasma cutter, and surprisingly long-lasting. I've actually used this on a ton of steel already, including many lengths of solid 1-inch round bar. Right, so I'm going to weld faces first, going from inside to outside, and then I'll go around everything clockwise. So interesting on that one, there was a very, very big gap. So I actually reduced the power to just 80%. Right, I've decided I want to redo this weld. It's not looking particularly nice, so I'm going to grind over it and then recut the groove. That is more like it. So what I've just used to hold that frame in place are these magnets. These don't look like much, but they have a clamping capacity of 100 pounds, and I find these incredibly useful. What's interesting though is you would never use these for general welding. That's because with general short circuit welding, the magnetic field actually interrupts the arc. It can actually ruin TIG welding completely. But with a laser, not a problem at all. Absolutely fine. Lovely, 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 lovely. Nice. I say that's going to be strong enough. So it's time to add some wheels, and I went out and managed to reclaim these. These are super robust, but they're a little bit too tall. So what I'm going to do is fabricate some L brackets. And to do that, I've got some other bits of kit to show you. So courtesy of Rob from Xtreme Plasma UK, we now have an arc droid. And to accompany Artec, the guys who I get all of my welding consumables from, have supplied me with their latest 50 amp P51D CNC compatible plasma torch. So first of all, I want to give accurate context to why I rate these companies. For a start, I got to meet these guys personally as they're quite local to me, just in Tewkesbury and in Gloucestershire. I've used Artec's equipment throughout my professional career, and we've always rated them for their service. They have designed and supply every single part that goes into this machine, and if anything breaks, they guarantee they can repair it. And the same goes for Rob and the guys at Xtreme Plasma. They're actually going to be at Makers Central this year, as at Birmingham NEC, hosted by Jimmy DeResta. Colin Furs will be there as well, guaranteed. So if you want to see this kind of kit up close, I recommend going there. So obviously eventually we're going to put the laser on this, and we'll directly compare the plasma to the laser. Right, so I've got this 6mm thick by 150mm wide flat bar. Just going to drop the wheel on it like so, and using a simple marker I'm just going to drop a point in all these holes and mark out where the edge is. And while I'm here, I'll mark out where that bend line is. Now I can easily drill this and cut it by hand, but using CNC is obviously quicker and repeatable. I'm going to quickly take this plasma torch off and attach on the stylus. I'm going to build my own attachment for the laser head eventually. So now let me show you how I'm going to use this to plot the holes and cuts. So this is the Arc Droid controller. So notice when I move the droid, it also shows me in real time the plot. So if I hover over one of these holes, I'm now going to zero it. This is going to be my place of datum. I'm going to put an 8.5mm hole and see my measurements here. If I go this way over the next hole, I've plotted exactly 80mm, which I believe is correct looking at the wheels here. All right, let's go up here. So that's all the holes mapped out. Now I want to do just one straight cut across here. So that's my first point. Now I've got my second point on the end there. Done. So to test this, I'm going to take off the stylus and put the Sharpie in. So I've set the cutting height to 0. This should now just draw on it. Let's hit run. What a lovely sound. Right, so has it done this accurately? Everything looks perfect, so let's get cutting for real. So let me quickly show you what's special about this plasma. The CNC interface cable simply plugs in the back end, and the arc droid has torch height control also. You can't just use any old plasma cutter in any old CNC machinery. It must be non-high frequency. So at the moment we're set to 40 amps, we can go all the way to 50, but for 6mm thick, 40 is just fine. So that's the first key setting. The next is air pressure. So we've got lots of little light bars across here. Notice that there's an arrow pointing to the center. You can see as the plasma torch is running, I've set it to about 70 psi. I can adjust it at the back of the machine. So that's obviously too much, 74, go down. 55 is too little. About 70 is what we want, I think. As soon as the plasma stops running, the pressure obviously builds up inside. But if you increase or decrease the amps, you need to adjust the air pressure. And I think it's so handy that Artec have come up with this solution, so you know exactly what air pressure to give your plasma torch. We also have a gouging feature, which we'll look at in a bit. And we can also click to tip saver. If I'm correct, you lose a tiny bit of cutting performance, but it makes the tips last a lot longer. Right then, let me show you what it can do. Right, so I forgot to change the Z height and it was moving the plate around. Never mind, it should still work fine. Let's try again. There we have it. That is the kind of cut quality you can expect. How accurate are these holes? Well, I set it to 8.5, 8.45 millimeters, just about perfect. The only thing to note though is they are slightly tapered. If we turn it around, they're only 7 millimeters on the back, but that's okay. I can just drill those through easily. So if we don't want to ream these out, we just simply have to make the holes a bit bigger. We've got the design file now, so let's just repeat it. If I just pull this plate 150 millimeters out, I've used some spacers here so I know it's completely square with the machine as well. So on the controller, I'll simply just click run again. Looking good. One of the best things about this though is because I'm in a small workshop, this is easily pack-awayable, clearing lots of space again. Right. I found some bolts, but they're all countersunk. Bit of extra work, but never mind. That looks smart, that. Right, time to cut some aluminium now. What I should have done is plotted some holes. Never mind, I'll do that on the next ones. But this was cut at 1,500 millimeters per minute. The edge profile is fairly neat, just a little bit furry underneath. So hopefully you can see all I've done is put down a couple of trestles, a few lengths of bar just to support the sheet in the right place, and away we go. We've got a full-on plasma table. So I need another exact bit of plate like that. Right, that should do. Right, so this time we should have some holes. There we are. Lovely job. And we'll use riv nuts. Now you guys don't necessarily have to use this, but future me always appreciates copper grease on a bolt. So if you were still wondering what it's like taking paint off stuff, pretty well is what I'd say. And these cable holders are made with this really rusty stuff. You can see it's actually quite heavily pitted. What the laser does is it kind of remelts all the oxide and then almost like fuses it to the surface, creating a very matte finish. And I would say it would take a paint quite well, very similar to shot blasting. I'll carry on with this with some better ventilation. This paint is about 100 years old, so it's probably got lead in it or something. So now behold, the finished rig. There is now a place for everything and everything has its place. So you might be wondering, how does it steer? Because there's no swivelly wheels. Well, because that gas bottle is so heavy at the back, it actually acts as counterweight. And so by using the handles, I can steer it like that. You can also see I've added this plastic wrap to the cable. That's because I find myself dragging and treading on this thing constantly. The torch was only supplied with this thin kind of webbing protecting the cables underneath, and so I wanted to make sure these are protected as much as possible, because the last thing you want is a break in the fibre optic cable. That spells trouble. And so I think this stuff will do the trick nicely. So then, you may have noticed this sheet of aluminium in the background. That's right, that is the right way to say it. So let's now interface this with the CNC machine. So to take this cover off, you need to pop this bit off the top. That was sat there, and I basically just heated it up with a heat gun and pried it off. But the only way of getting the cover off is if we undo these two bolts first. Right, so I've removed all the little screws. Cover should now simply lift off. So this block here is the actual laser source. So this is what creates the laser light, which goes into this optical cable here. So I've turned it around now. This is the main power supply, and this creates DC 63 volts at 48 amps. And then you've got your main motherboard and everything down here. So on the back of the machine, we've got all these ports. This is your power in, this one goes to the feeder, and this is the gas. But then they've given us these three ports, which do optional extras. So if we look on the inside though, you can see that the exterior control has nothing attached to it. The bottom port though has about 3 wires attached to it, but also the RJ45 has nothing on it either. So the cable that is attached has some Chinese writing on it down there, and according to Google Translate that says external control cable. That's a good sign. So I want to point out that I don't actually know what I'm looking at, but with the help of AI we can kind of diagnose these ourselves anyway. So what I think I've figured out is one of these wires is a ground, the other is an input, and the other is an output signal. Possibly an RX and a TX connection, like what you would find in an Arduino. To properly figure that out to get some interface with the machine though, I need some other specialist equipment. And it's at this stage, which probably a lot of you will as well, say, no thanks, I will not touch my very expensive machine anymore. But I just thought it was interesting to show you that on my machine I've got so many ports that are not used. Another thing to point out is most of this build is one giant piece of aluminium, and on the back of it a set of very powerful fans. Interestingly, the fibre optic cable goes in a coil right connected to the side on it, just with a bit of tape. I don't know why it's all coiled like that. Maybe it's something special about fibre optics, but I thought I'd share that with you. So I've put the cover back on. I think our only option now is to look at the torch. I've cut back this protective sleeve. Now I can undo these little screws. Right, try your best not to lose your screws. I've lost mine already. That pops off. Now this should just come off like so. So as you can see, our job here isn't so simple either. It's not the case of a simple on-off switch leading back to the motherboard. Instead, we've got all sorts of signals going to different relays. And the overcomplexity, I believe, is something to do with this button here, which is very, very annoying. I very much wish this didn't exist, because I'm constantly clicking it, changing all my settings. That's what it's meant to do. It's meant to switch between some presets, but I don't like it. Anyway, I do have an idea, which I hope will work, and it should just mean soldering a connection straight off this button switch to this little jack port, and then from here I can go straight to the arc droid. Right, so then the first thing I'm going to do is remove this switch. So unsoldering all 4 of those connections. If I can, using a bit of scrap wire, just get rid of some of that excess solder. So I've already soldered wires to the mini jack port, and that should go about there like so. But just to make sure that these bare wire connections don't interfere with anything else, because that would be a disaster, I'll try and attach a bit of shrink wrap on the back of it. Something like that will do nicely. And I don't think it matters which way round these wires go. We'll soon find out anyway. There we go. Not the neatest of soldering, but it should work fine. Right, so I've opened up the button hole. That's now 6mm wide, but recessed. Question is, does everything fit okay? Well, that is a bit tight, but I would say that's quite successful. Right, there we go. Let's link it to ArcDroid. So in my CAD software, I've knocked up this very simple bracket. I've flattened it out and saved the shape as a DXF. DXFs are the type of file that are used for CNC cutting. And then using the arc droid and the plasma, I cut out the shapes to create the bracket. This is not a perfect design, there's lots to improve. Anyway, let's rig it together and see if this thing works. Well, it's on there. There we go. So I've soldered the wires onto the jack lead. It can just get covered now. And then simply inserted. So very simply, I've attached the laser interface onto the torch. It doesn't matter which wire's which. It's about closing that connection. So we'll do the very first cut on this aluminium, simply because it's already out, we're already set up. Thing that's finally worked. There we go. Well, that is extremely cool. You see, it's not done it perfectly though, which is a shame. Oh dear. So I think I've pushed everything to the absolute limit there. This is 2mm thick aluminium, and some of these shapes are less than 1 millimeter in width. And with aluminium, it actually leaves quite a lot of dross behind, which is why it's getting stuck. I tried using pure nitrogen, but it actually didn't give me as good a finish. So I'm going to continue doing all of the cutting just using compressed air. What I will say though is I had a few issues with the arc droid. This file is actually way too big for it. In the end, I had to split it into 2 separate files, so the inside and the outside. So it's not a bad amount of detail that you can get done, but it does have its limits. Otherwise, we should connect arc droid to a computer and then control it using CAM software. Another thing to consider is look what it's done to my poor floor. It's absolutely exploded my slabs. I mean, admittedly, it was already cracked before, but all of this damage, that is all laser. And we will explore further laser dangers shortly. Remaining on the subject of aluminium, I would actually like to do a weld test. That's because I recently watched one of my favourite YouTubers. If you want to learn aluminium TIG welding, this guy is actually really good. However, very recently, he's been saying awful things about laser welding. So I'd like to settle that debate and do my own test. But then I want to start cutting steel, stainless steel, brass, copper, thin brass, thin stainless steel, acrylic, wood, and whatever else I can find to satisfy the demand. I'm probably not going to be able to fit all this in this video. I need to repair some holes on my truck also. But right now, I've got a very special commission. My wife has asked me if I would cut a load of these out. She's part of the Spinners and Weavers Guild and has been instructed to show the children at the local show how to do it. Anyway, the show is tomorrow, so I've eaten my blueberry wheats, and so we'll recycle it into weaving discs. So Arc Droid's got a really nice system to create a nice mesh of parts. I've set the speed to 2000 millimeters per minute. Arc Droid can move a lot faster than that, but I'm about to show you why you wouldn't want to. Right, so the laser is on just 10% power. Let me show you how quickly it will run. So you can see I did it just directly onto my steel table. It's not actually hurting the table at all, it's just clearing some of the rust off it. It does leave it a little bit smoky on the back though. But the problem is, because the laser kind of probes, you need to have something substantial to kind of take the weight. What it's doing is gauging the perfect height to get a proper pierce. And whilst that works really well on steel, not so good for thin stuff. But this test revealed something important. See how wobbly these lines are just there? Those aren't meant to be wobbly, those are meant to be straight. So Arc Droid does struggle with high speed cutting. I can get this laser cutting at over 5000 millimeters per minute, but the Arc Droid has limited me to just 2000 millimeters per minute. Otherwise this wobbling gets even worse. Now if I use the Arc Droid for its intended purpose, like cutting 20mm 1-inch thick plate with a plasma torch, then it requires steady slow speeds. But if we want high-speed laser cutting, then we need a much stiffer gantry. Very quickly then, let's do some aluminium. And I'm using the exact same settings as steel, except I've changed the gas to pure argon. So this specific grade of aluminium is 1050H14. I'm not too sure what the filler wire is. I believe it's 4043, but it doesn't have a label on it, so I don't know. So because people keep saying it, I'm just going to warm it up first. That should be enough. So let's give that a go. Turn that around, do the other side. It's saying it's not that hot, but it is very reflective though. There is a setting for that, but I haven't figured it out yet. Anyone who's actually worked with aluminium will understand that if this has worked well, it's a complete game changer as far as a lot of things go. I mean, that's why I bought that big sheet. I've got a lot of projects I want to make out of aluminium. So then, let's break it. Oh, I did that. Well, there you go. So I don't know if you can see that, but that is all the way around the weld that is breaking, but definitely not the weld itself. Now then, the moment some of you have been waiting for. I've got another battery system I'm supposed to be reviewing. I know, more expensive stuff none of us can afford. When it comes to money, I'm tighter than a gnat's colon. But because I'm a YouTuber, I get given this stuff, so the least I can do is objectively figure it out for you guys. But hopefully this is going to be interesting. If we plug the laser into the battery, can it be portable? And I'm thinking truck mounted. So plug you in there. I'm going to be testing all of my batteries in a new video coming, mainly for my gasification projects. That's turning more wood and charcoal into electricity. But we'll give it all a test on solar and everything as well. I found this to do a test on. Forgot it also requires compressed air. Otherwise it doesn't work. I have got a mini compressor though to go outside. Here we go. Now try this. We're battery powered! Right, so keep an eye on the wattage for me and see how this performs. I'll have to check the footage. Right, so that's exciting. And if you're interested, this is the Anker Solix F2000. It is pricey, but it's a good bit of kit. So we actually had some bad storms not long ago in the UK, and I lent the Anker out to my in-laws to keep their fridges and freezers going. They had a complete blackout and didn't have power for several days, and this, well, it saved the day. But now let's take it out and destroy something. So I've brought you into my polytunnel where I'm learning to grow my own food for the coming global famine. That's in light of the rapid extinction of pollinating insects. I'm actually learning to be a beekeeper too, but that's a topic for another day. But as most gardeners know, weeding can actually be back-breaking work. So how about using lasers to decimate weeds with pinpoint accuracy? So believe it or not, the agricultural industry has already adopted this technology. So the way it works is they use AI recognition technology and robotics to discriminate weeds and destroy them. So if these guys can do that with plants, imagine what the military has to do that with people. So I want to point out that in no way I'm recommending what I'm about to do. Using a high-powered laser outside of a secure facility is extremely risky. So these type of lasers have been used in professional industry for a number of years now. But to use one, you'll need Class 4 laser safety certification. But technically, if you're working in industry, you also need an abrasive wheels certification to use an angle grinder. But we all know we can pop to our local DIY store and pick up a grinder anyway, which obviously leads to thousands of cases of people getting stuff stuck in their eye. And the laser is no exception. So basically, I'm going to be treating this like a firearm. I'm going to make sure the safety is always on when I'm not using it, and I'm never going to point it in a way that could cause harm. So basically, if you're using a laser, you should be doing a risk assessment and take the highest standard of precautions. But anyway, in the name of science and entertainment, let's destroy stuff. So I've linked to the laser a small 24-litre compressor. With the emergency stop button on, I can test the gas by pressing this button. It just needs enough to overcome the safety features. And even now the laser won't operate until I've put the ground clamp on. This is simply another safety feature. So what you're meant to do is have this in contact with what you're welding. And so if you release contact with what you're welding, it cuts the circuit. So anyway, I've set to 100% power, 200 hertz, 8mm beam. Let's kill weeds. So as you can see, between my lettuce and tomatoes, I've got chickweed and fireweed. There's also nettles in amongst there as well. Let's see if I can clear all this up. Right, I don't feel like that did much, so I've reduced the laser width to 0. See if we can be a bit more pinpointy. Well, that's better. Right, it's definitely working. However, when the cooling gets triggered, we're drawing way too much power. So this is only good for short bursts, really. But that might be fine enough. So it's definitely worked, but I'm a little bit underwhelmed by the weeding action. I think we should try something a little bit more exciting. Well then, this is the experiment I'm most excited about. It's also the one that has most people concerned when I've told them my idea. But anyway, I've blown the budget and I've bought an FPV drone. So FPV meaning it's got a camera and I can actually put this on a headset. Except I'll need to have one eye on the laser, so I won't be doing that. But basically, I'm going to fly this as high as I can and see what distance it takes for me to shoot this down. But I want to emphasize again, you should not be doing this. And interestingly, the police force already have lasers that can shoot these. However, I may or may not be told off for doing this, and therefore I cannot recommend you try this. Well, I've only got one attempt to try, then let's hope it works. Start setting this up. Right then. There's a bit of a wind. I'm also checking for birds. Right, flying drone, testing laser, ready. Right, I want it to just go straight up. Oh my gosh, that's flying around everywhere. Well, it turns out I am rubbish at flying drones. And I believe there is a way of getting this to stay straight, so we'll try again. Just want it to hover. This is so hard. Oh my gosh. Oh, I've lost imagery. Right, not the best start then. Let's see if I can improve on that. Where are you going? Dear me. I think there's something wrong with the propellers now, actually. Turns out you don't need a laser, you just need an idiot like me to fly it. Oh. Think we're getting there. Think we're getting there. No. No. Come back. Oh, we are now next door. Hang on. Switch to my last battery. Yes. Come on. Come to daddy. Come to daddy. There you are. Come on. Literally firing at you. There's nothing coming out. Definitely a laser there. I mean, how can you be a bad shot with a laser? This is an actual Ukraine drone. Be a goner. Right, well, that was a failed attempt. And I'm sure I had good line of sight on it as well. So that was incredibly frustrating. I was sure I was hitting it dead on. So what I decided to do now is set up a stationary target at a set range. Because I really want to know what distance is deadly. So I've set up a little box. I've got the action camera pointing towards it. So according to the laser rangefinder, that's 21.5 meters away. Okay, we are now armed. Now interesting, I can't see the laser dot on it. Let's see how this works. Nothing. Disappointing. Let's move you a bit closer. Try there. That should do. Right, that's just 13 meters now. Let's just check on the ground. Yeah, that definitely works. Alright, let's move you a bit closer again. This has taken all the coolness out. Right, where are we now? 7 meters. Test on the ground. Yes. Nothing. Well, this is a bit of a disappointing range now, isn't it? 3.5 meters. I'm wearing my glasses just in case. Nothing. Maybe it's the white is reflecting. I didn't even think of that. Alright, well, let's turn it around then. Oh, it feels warm. Testing. Hey, finally. At 3.5 meters. Right, let's try a bit further away then. 9.8 meters. Call it 10. If I slowly just bring the laser downwards. Well, it's not smoking until I'm right close. Well, I do apologise. That was very anticlimactic, wasn't it? Well, in that case, there's just one experiment left to do. Well, what would happen if we're laser welding away and I accidentally slip and laser into my hand? Alright, so I'm really sorry and I apologise if you're Ukrainian, Russian, from New Jersey, or even if you're a Birmingham Blade Runner. These lasers will not do the trick. But I think for most people that would be considered a good thing. But now, if any of you have seen the induction forge video that I did, you know what to expect. And if you're slightly squeamish or of a nervous disposition, I recommend that you look away now. So in the induction forge video, I was wearing a wedding ring. So we wanted to test to see what would happen if we accidentally put a hand in the coil. And so in this case, we're going to test to see what happens if the laser hits my hand after welding. Now, are you sure you want to watch this? Look away now. 3, 2, 1. Oh my goodness me! Ah! Oh no! And you know something? It's actually quite hard to get a sausage inside a glove. And I should know, I've got 4 kids. Now imagine if that was actually your finger. I think this might actually put me off my dinner tonight. So, moral of the story, don't put your fingers where you wouldn't put your wiener.
My wiener!
Oh, I would say that would be very, very painful. So I take it there are still a lot of unanswered questions about this technology. I think we want to test a wider range of materials, including cutting steel. And I know someone's going to point out, will it go on a regular gerbil machine? This is one that I kept for a future project. I think this had like a 10-watt laser on it at some point. Got its own controller, a bit like the Arc Droid, except you can actually get one of these for about 120 quid. It is more of a challenge for the practical amongst us, but you do get what you pay for. And on a side note, Laser Labs have told me that they're trying to develop their own CNC as well. Probably something competitive to X-Tool's new release. But that's enough for today. I will do my very best to answer all your questions in the comments section below. If you did enjoy this video, can I recommend this one? But if not, can I recommend that you stop watching YouTube, get out there in the real world and forge for yourself a life worth living. I'll see you in the next episode. Bye-bye.